Start again. There we go, recording in progress. So good morning. Today, we will continue on with time APIs in Python, in particular, the time date, or is it date time? I always kind of mix the words backwards. The date time APIs. But before we begin, the usual administrative stuff, project number 2A will be due on the 12th of March, and that is for you to have a wonderful spring break. I don't assign work over breaks, and that goes back to when I was an undergrad. Long story short, I got a massive homework assignment over Thanksgiving. I wasn't able to participate with my family, and my mother was so displeased at the time. She was going to call up my instructor and tell him what she thought. And I begged and pleaded with her, please, I don't want to get kicked out of school for what you're going to say. Don't call her. And I vowed then one day, if I ever become a professor, I'm not going to assign work over breaks. And so I don't assign work over breaks. So please make sure you enjoy yourself, unwind, go someplace warm if you can, go home, which is also warm in a different way if you're from a colder region. But nonetheless, I can't promise for my colleagues, but certainly I don't assign work over breaks. So that being said, I organized the course specifically so that I can make sure I'm staying on schedule and plan with material so that you don't have work over breaks. Okay. And so the reading has changed. Again, the reading is timed or has a deadline to help you with pacing. And so it's on purpose that I have this particular part dated as the 15th of March, which is the Wednesday after you get back, that Sunday night or that Monday. Any questions? No? All right. So why don't we jump right in? So when we last met on Monday, at least for course material, we talked about the importance of time, and we motivated it at a high level. And we started out with this visualization of something called Tolkien's theorem. And we said, without seeing the system itself, the swing in this example, just by having two measurements of position in the x direction and velocity, as you see at the inset here, these two graphs, just by having measurements in time, you can recover all sorts of facts about the dynamic behavior of a system. And so after all, that's really what we're concerned with when we do analysis on time-based data, so-called time series or so-called temporal data. And so we talked about this idea of purely just from these observations, you can recover, for example, these repeating states representing the two extremes of the swing, as well as that bottom middle part of the motion of the swing. Okay. So then, first, any questions? No? And there's a rich set of theories and area of study in dynamical systems. If you're interested, I can tell you a little more about that. We talked about financial markets, and in financial markets, of course, these quantities of interest, stocks, commodities, etc., they vary in time, right? They're traded by the minute, by the second, over time, and so people are certainly very concerned with the dynamic behavior of these particular securities. If you do it right or make good observations about it, certainly it's hard to predict, but certainly you can use what you know about this time-based or dynamical behavior or dynamic behavior to make a lot of money potentially. And so important are these behaviors in the value or price of a stock or security over time that they being the finance community, looks for various pathologies or patterns in the temporal behavior. And this is just a very small smattering of that. Lots and lots of different temporal behaviors that they use, and they detect them with computer algorithms and use that as the basis for triggering high frequency trading or automatic trades. And so this isn't my background. My interest is in statistical descriptions and predictions and things like that. And I'm sure if you went to grad school in computational finance, you'd learn all about the models and how temporal systems for both individual securities as well as sets or baskets of securities, how they work over time. Okay, any questions? Yeah. So then we also talked about customer behavior. And we showed a video of an overhead camera view instrumenting the so-called entry box of a retail concern. And the system counted customers, not their particular identity, but just their presence as they made their way both into the store as well as out of the store. And using a system like that in time, you can calculate the number of people in the store and then associating those numbers of people in the store with the number of sales, both the product counts and the product and the revenue collected, you can use that information for all sorts of useful things, such as modeling the behavior, the customer behavior of your store, which is immensely useful for things like deciding your staffing levels, projecting out the revenue you think you're going to earn, influencing purchasing decisions, etc. Okay, any questions about this? Does that make sense? And so in this case, we make an assumption, an educated guess of what the form of these of the stochasticity in these observations are, the variables, the number of customer accounts, and then we use that educated guess to mimic or model the behavior based on the observations that we have. We also talked about what is called or so-called precision agriculture. And with that, we're taking temporal measurements of various factors that are important to the quality and yield of agricultural products. And so one of the added benefits of that is certainly you know the condition of what's happening at a more fine scale granularity. So instead of looking at entire regions via satellite, you're considering more localized by the field. And the goal with this research is to get down as close as possible to a plant level. And so one of the benefits of this is if you know the temporal behavior of what's happening with these important measurements, important to yield and quality, when you apply interventions, be that nutrients, pesticides, or what have you, you can more quickly see the impact or measure, quantify the impact of your interventions. One of the big ones is alleviating or reducing the amount of pesticides applied, but also the amount of nutrients. And too many nutrients can lead to something called nitrogen runoff, which can poison water supplies. Any questions? Does that make sense? Okay. And so with these sensor measurements in precision agriculture, one of the issues that is fixed with another type of interpolation we haven't discussed is what's called data integration. And with sensors, when you're measuring phenomena from the real world, these sensors return back measurements at characteristic rates, but these rates of measurement are not the same. And so we depicted that here in this schematic. Imagine you're measuring temperature every 10 minutes, and it's usually more fine-grained than that. It's usually a few times a minute. And imagine you're also measuring wind speed every 15 minutes. And so when we saw data sets and we looked at so-called random vectors, we assumed that all of the measurements for each one of our random variables was available at the same time. But that's not true in practice. And so depicted here at some time step, TI, imagine we had a temperature measurement, and at that time, we want a random vector that includes temperature and wind speed, but there's a problem because we don't have a wind speed available. It doesn't arrive every 10 minutes. And so you can use probability distributions to do interpolation. This particular one's called the Gaussian process or Kalman filter to effectively give you a measurement in the absence of a real measurement from your sensor. And then when your sensor measurement arrives, you then update your distribution because that's new information. And then it's available for the next ask or query for what is the current wind speed. Okay, and we'll talk about that towards the end of the semester. And any questions? Does that make sense? All right. And so we'll start out with time representation. And time, or many things time, not all things time, in Python are available in the so-called DateTime library. And so this DateTime library also is a companion to something called the time delta library. Now, DateTime gives you representations of time along various granularities. It can be along years, along months, along quarters, along seconds, along minutes, and so forth. And so with the DateTime library, you're representing specific instance in time. It's today's Friday, Friday, March 3rd, 2023 at 9:05 or 9:10 or whatever it is. And so this time delta also traffics in time, but it represents a duration. 5 minutes have transpired. And together with these, we can do all sorts of very useful things, useful to the analysis of time series or time-based data. And so you can also represent fixed periods of time on various levels of granularity, as I alluded to before, along months, years, seconds, microseconds, and so forth. You can also represent intervals in time. Give me all of the dates on a daily basis between some starting point in time and some ending point in time. Now, the nice thing about this is that it gives you or implements for you the algebra. You don't have to sit there and if you want to know the number, the amount of time that transpired between some ending date and some starting date, it'll do all the calculation for you, including leap years, for example. And so that's kind of nice, and it can be very useful for all sorts of analyses on temporal data. And so you have lots of useful APIs for what I'll call slicing. Now, this is different slicing from NumPy slicing and like extracting a column or a subrectangle from a data frame. But this type of slicing talks about taking particular increments in time from one starting point to another ending point, and then you can now re-aggregate them. So you can say, okay, well, if I had all of the days from January 1st in 2022 to June 1st, 2022, instead of expressing it in increments of days, express it as increments of hours, and it'll do all of that calculation for you. So not only can you chop up increments or intervals in time, you can also cast them on a different scale, and it'll do all of that work for you. It's immensely useful. You can resample, and that resampling is a specific API call that allows you to transform from one boundary, say year to year, to another boundary, day to day, minute to minute, etc. And so today we'll look at examples of most of these APIs. Any questions? That makes sense? No? And so let's start out with the imports. It's always useful to import NumPy. I just kind of do that in my muscle memory without thinking about it. And Pandas, now that we have introduced Pandas, as you've seen, it's immensely useful for slicing and manipulating data. But Pandas is limited to two-dimensional data, table form data, not arbitrary n-dimensional data. But nonetheless, we import from the DateTime module the date object as well as the time object. Now, of course, date and time are, as the names appear, date represents the year, the month, and the day. So today is March 3rd, 2023. And time is represented as the hour, the minute, the second, and optionally the microsecond. Now, when you represent these constructs and you print them out, as we see here, we construct an instance of a date object. I really wish I had a better way to point. I hate this little red dot. You construct an instance of a date object. Here, it's January 15th, 2022. And then we construct a time object. We can print them out. And the print method in these objects will produce the strings that you would expect. In the first case, for the date, we have 2022-01-15. And for the time, we have 13-25-45. And 125-123 is the number of microseconds. Now, of course, when you do this, you notice it's in a default format. But one of the options that you can specify, and we won't go over all of those umpteen many options, you can specify the format. Now, it's uniquely North American thing to represent the date by the year first and the month, then the day. But there are other locales that represent dates in other formats, and that cert format is certainly something that you can change when you construct your date object. Any questions? Does that make sense? Yeah. All right. And so you might say, gosh, well, I don't really find myself expressing dates and times down to the microsecond level, and you're not required to do that. And so you can also truncate your representation, and I'm kind of jumping ahead. I forgot about this slide. One of the things you can do, of course, certainly when you're running a program, your computer has a so-called system clock, and that system clock communicates over the network with very accurate clocks through a time protocol, and it maintains its understanding of the current time. So in the DateTime object here, here we have DateTime. Now, DateTime is just a combination of the date object and the time object. And so the date time brings together the year, the month, the day, as well as the hour, minute, second, and microsecond. And so in this example, we import the date time object from the date time module. Now, it's kind of weird to have date time object and it's called the date time module, but hey, I don't know why they designed it that way. Go figure. But nonetheless, we take our date time object, and one of the things we can ask it is give me the time right now. So underneath the covers in the Python runtime, it'll go to your system clock and it'll say, hey, give me the current date time. Okay. Now, once it gets that, then based on the format that you've specified, in this case, when I say now, it's going to assume whatever the default format is. And again, if you go to the library, the documentation for the DateTime library, it'll show you the probably 100 different options easily that you can have for this. So it'll take the default format, which is the US North American format. And if you're curious, if you had the, say, German version of Microsoft Windows, one of the things they set when you install your operating system is a so-called locale. And wrapped in that are things like the date format. And so if you're running Windows in German, it would get the European format for date, and that would be the default. But you can still programmatically through the API tell it what format to use, even if it doesn't match the locale for your particular operating system. Okay, so we construct our DateTime object, and we give it the year, month, day, hour, minute, second, and microseconds. And then when we print it out, you can see it prints out the date portion, 22, 10, 13 in this case. It's just an example, and the time portion right next to it. Okay. Any questions? Does that make sense? Yes. Yes. When you say now. Yeah. Yes. So I know Mhm. Ah, that's ah, this is wall clock time, but if you're doing performance measurement, and it just so happens when my second job out of undergrad, when I was in industry, I was on the performance benchmarking team. So to answer your question, you want to use the operating system facilities, and there are two different types of time. There's wall time, which is just the duration that has transpired, but then there's actually CPU time, right? And so with CPU time, for everyone's benefit, when you characterize a computation, there's the what's called the compute bound parts of your process, which are the calculations. And then there's the IO bound parts of your calculations where it's waiting for like the disk to spin up or for data to come across the network. And so typically when you talk about performance, you amortize it in terms of that portion spent on this, excuse me, I felt a cough coming while mid-sentence. That portion spent on the CPU, that portion spent waiting for IO, and then the wall clock time. So oftentimes you rely on the operating system facility because included in that CPU time on the front end, there's the loading of the program from disk into memory, and then there's a swapping in and out. So they often rely more for benchmarking on the OS facilities, but not the facilities in the program runtime in practice. But to answer your specific question, it'll still, for the purposes of what we do in this class, it'll give you the wall clock time, which is that time that's transpired between when you started the process, everything that you did between calling now and then if you called now afterwards. And it'll give you like a back of the envelope, but in practice for scaling in industry, they usually rely on the OS. And that's not to say you can, I'm like 100% sure you can find timing facilities, libraries in Python, but for really they just kind of call out to some C++ object underneath the covers. Did I answer your question? Okay. Any other questions? All right. And so as you can see, excuse me, when this date time is called, you see the date portion alongside the time portion. And so certainly you might not really care to represent all of the units like microseconds and minutes when you represent time. And so if you construct a datetime object, in this example, leaving out the microseconds portion, and it truncates in the representation when you print out, because it's giving you that default that you would fill in. It still needs to display something, right? And so in this case, you specify the year, month, day, hour, and minute, and you can see that the microsecond portion, that part after the decimal point, is no longer there, right? It's effectively 0. Okay. Moreover, if, for example, you constructed a date time and you only gave it the date portions, year, month, and day, it still needs to represent the time portion. So it fills in a 0 default if you don't specify that for the date time. Now, certainly, if you're wondering why would I just use the date object? Well, that's just to show you that the defaults are still there underneath the covers. Okay. Any questions? Yeah. So you can represent different resolutions in time, but based on the object that you're using, it still needs to provide a default value because underneath the covers, that object has placeholders for each one of those resolutions, the microseconds, the hours, and the minutes and the seconds. Okay. And so another thing that I alluded to before was you have the datetime algebra, which is given to you for free, so to speak, just by using the library. And so in this case, we set a datetime object, and we only fill in the date portions, the year, the month, and the day. So it's going to give the default values for the time portion. And then we ask datetime, give me a datetime object corresponding to right now, goes out to the system clock in your operating system. And so if we compute the difference, it goes ahead and does those calculations for you, representing leap years appropriately. I haven't tested if it does daylight savings, which would be an interesting thing to test because the hours shift. That would be, I don't really know the answer to that one if you're curious. Any questions? No? All right. And so another thing that you can use is this so-called time delta. And the time delta isn't a specific instant in time. It's an amount of time, a duration in time. So like 5 seconds has passed by, for example. Now, in this case, I construct a datetime object and I ask it, give me a datetime instance for right now, goes to the system clock, returns it to me, and I call that or assign that to variable now. And then I construct a time delta, and I say, okay, time delta, I want you to represent for me a duration of 7 days. So now when I say a duration of 7 days, I can take that duration and use that also with my datetime algebra. So I can say now minus this duration of 7 days. And so that would tell me what was the date and the time 1 week prior to that particular instant in time that is right now. Okay, any questions? That makes sense? And so you can see if right now, yes, I think I did this for assuming today. About 7 days ago would be February 24th around 9 o'clock. And I was assuming 9 o'clock and 7 seconds was now. Okay, any questions? And you can see it gives it to you, this time delta, when it does that time algebra it gives you the resolution down to the microsecond if you chose that. So I could say time delta is 7 days, 3 hours, 2 seconds, and 10 microseconds, and it'll do that algebra for you. Immensely useful. Not that you couldn't do it yourself, but why spend your time doing it, to be honest with you? Okay, any questions? Does that make sense? And so another thing that you can do, now why this is in Pandas, again, I don't have an answer for you. I would assume that because you're constructing a data structure, a table, that they said, let's benefit from all of these useful methods in Pandas rather than doing it separately in the DateTime API. But you'd have to reserve that question for someone who works on the API. But nonetheless, related to the DateTime library, in Pandas, you can ask it to construct a data frame for you that represents a range of dates. And you can also optionally specify the date format that you want it to use. Now, in this case, Pandas does inference, right? It looks at what you're asking it, and based on what you're asking it, it makes an educated guess, not really a guess, it's following an algorithm about what the increment is when you give it this start point and this end point for the date range. Now, in this case, the default behavior is to increment on days, but you can override that default to increment along all sorts of boundaries, like years, if you chose to. And so here we have a start date of January 1st in 2021 and an end date of December 31st of 2021. And when we do this, it gives us a date time index, not a data frame. And if we were to print that out, we can see all of the entries are strings in this date time index. And so this would be very useful for what we did in project number 1, where you constructed all of this by hand. So you can imagine then underneath the covers, based on the start, based on the end, it'll choose a granularity and it'll loop appropriately and append strings to construct this representation. Okay. Any questions about this? Does that make sense? Okay. So you can also specify date ranges, not just for days. You can do it for years. You can do it for minutes. You can do it for all sorts of boundaries. And again, there are hundreds of different options that I can't possibly cover in a semester. And so when we do this in the Pandas APIs, you'll see here when we print out the date time index, it tells you the data type, and this is in nanoseconds. So you have nanosecond base resolution when you specify these ranges, if you choose to, where nanosecond is 10 to the minus 9 power. Okay, so you can get very, very fine grained in this. If you have a reason to represent a range in nanoseconds, you're able to go ahead and do that. Okay, any questions? No? All right. And so let's look at aggregation. This is where it gets really interesting. And with this aggregation, you can do all sorts of stuff. Again, we're going to construct a date time index. And so we go to Pandas and we ask for a date range, and again, from January 1st, 2021 to December 31st, 2021. You have use of all of the useful APIs that you would typically associate with a data frame. But this is a date time index, and it just happens to be in the Pandas API and not the date time. So here I have my dates on a daily basis from January to the end of December. And now I might want to know, what is the maximum date? What is the minimum date? What is the median date? Or maybe you want to know what the quartiles are, the 25%, right? Now it doesn't have a quartiles function, it has a quintile. A quartile is nothing more than a quintile at multiples of 25%, right? Quintile is the generalization. But nonetheless, you have other types of statistics that you can calculate on date time index entries to do all sorts of things in terms of ordering and quartiles and stuff like that. Okay, any questions? Does that make sense? All right. Now, in this example, we're going to pull in a CSV file. We're going to read this into memory to illustrate a bunch of important concepts about aggregation. And so this particular data set is publicly available, so-called lightweight vehicle sales. The units, I think they're dollars. I can't remember what they are. But nonetheless, we're going to pull this into memory into a data frame using Pandas. And one of the things you'll see here, these two options, index underscore column, and it gives the name of a column or a series, if you will, in the frame. And then it says parse dates equals true. And so one of the things that's important when you pull in temporal data is you often want to replace the default index, that position into each one of the series corresponding to the row. You want to rename them or override the default with the date itself. Because after all, each one of those entries, those rows in the data frame, is a timestamp, right? You took a measurement at a particular time, another measurement at another time. And so often you see with time-based data, particularly things that you read in from a data file, in this case CSV, you often want to replace that default index 0, 1, 2, 3, 4 with the date associated with that measurement. And so here we say index column equals date. You give the column name. And again, that's case sensitive because it represents a key in a dictionary. So you have to use the exact capitalization when you say index column. And then parse dates, you're telling your call, you're instructing the API call how to interpret the date format. Now, if we say parse dates, it says, yeah, go ahead, I'll parse the dates, and I'm going to use the default format. But optionally, you could override that default format from, in this case, the North American format, which is year, month, day, to some other format, depending on the locale and the encoding for that date field. And so let's say if you had a European colleague that you were collaborating with in some digital farm management project, and their sensors were date stamping using their date representation, their CSV file would assume the date is in a different format, and you'd have to account for that. And you do that as an option on the read CSV API call on the data frame or in Pandas. Any questions? Does that make sense? So here, we're just reading it into memory and taking the shape. This particular data frame or data set has 561 rows and 2 columns, namely the date column and the actual measurement column itself. Now, consequently, this set of measurements is from the 1st of January 1976 to the 1st of September 2022. All right, any questions? No? All right. And so now, suppose you wanted to produce a financial report. It's very typical to want to know what are the totals for certain variables, certain measurements on different time boundaries. You might want to know, for example, what are the monthly sales numbers? What are the annual sales numbers? Or if you're publicly reporting on to the Securities and Exchange Commission, what are the quarterly earnings which publicly traded companies are required to report? So here we read in our data, our lightweight vehicle sales, again, overriding the default index with the date label. And now we're calling this a resample. And this resample, then it says, okay, well, I'm going to change the way I aggregate my data. And what this resample does is constructs an instance of a so-called DateTime index resampler. So it takes all of the data from your data frame and it puts it in this big container. So it makes a copy, and this big container can then chop up your data in units along certain boundaries. Now, in this case, when I call resample, this option rule, I specify rule equals Y. That means take my original data based on its date and aggregate together all of those rows that have the same year field in the date. Does that make sense? Okay, so that means everything from 1976 is going to be put together in one list. Everything from 1977 is put together in another list, and so forth. Okay, so I can do this on a year boundary, monthly boundary, weekly boundary, quarterly boundary, lots of options available to you. Now, once you have this date time index resampler, you need to tell it to do something, right? Because it's just a container. It can't actually give you information. It does something with this information. So one of the things you can do is say, okay, take my aggregations, in this case, on a yearly or annual basis, and go ahead and compute the sample mean for each year's worth of data. So then you can imagine algorithmically, it goes through each one of these lists, the list for 1976, the list of numbers for 1977, the list of numbers for 1978, and so forth. And it goes ahead and computes the mean. So once you do this, you get back another data frame. And this data frame now has entries for each year. And in this example, we print out the first 5 entries in that reaggregation on a yearly basis. So going back, we said this was from 1976 to 1922. And one of the things you'll notice here is when we print out this data frame, we see an entry for 1976, 12/31, December 31st, 1977, December 31st. Each year, in kind, December 31st. Now, when you do this mean, what it's reporting to you is the mean for the year ended, and the year ends on December 31st for 1976, 77, 78, 79, etc. And if you printed out the whole thing, it would go up to 2022. Okay. Any questions? Does that make sense? Okay. So you can imagine what you'd have to do if you implemented this yourself, right? Imagine looping and string comparing. All this work is done for you in Pandas. Okay. So another thing we can do, we take the same lightweight vehicle sales, and maybe we want to produce a report that talks about the quarterly performance. Businesses often talk about quarterly performance. The quarter is every 3 months in your fiscal year. And so in that case, we do a resample, create one of these date time resampler, index resampler objects, and it aggregates now every 3 months. The first quarter, or Q1, is January to March. The next is April to end of June. I can never do it off the top of my head, but it's every 3 months of aggregation. And so here we take one of these objects and we aggregate every 3 months worth of measurements. And then here we say compute the mean. We get back a data frame filled with these means. And you'll notice here the default index, it's still a date label, but it's changed. The first date label is 1976, March 31st. That's the end of the first quarter, Q1. So it's Q1's worth of data. We've taken the mean. And you'll notice every subsequent default index, which is the date label, we have June 30th. We have September 30th, which is Q3. We have December 31st, which is the end of Q4. Does that make sense? Any questions? So it does that aggregation for you, and it also adjusts the date labels as appropriate. Okay. So when we talked about securities, we displayed this graph, and this is from Yahoo Finance, finance.yahoo.com. You can go on there, enter in the special name or ticker symbol, as it's called, for a publicly traded company, and it'll bring up a stock chart for whatever time boundary you select. Typically, you can select a day, a month, a quarter, a year, or what's called year to date, which is since the company first became publicly traded. And so we said at that time, the blue figure or the blue graph represents the closing price, but you can certainly go into the API and change what's being reported. And these bars down below, we said were called the volume underlay, and it represents the total number of sales or purchases of these securities. And so here we're going to take on Yahoo Finance, and you can go either Investopedia or Yahoo Finance. There are a lot of publicly available web services out there. And you can go ahead and say, give me the data for a particular security over a particular span of time. And so in this case, we have some Apple stock, and this Apple stock, again, any security is reported for each trading day. So if you had a federal holiday, that wouldn't be one of the trading days. It's only 5 days a week because that's when business is open, minus any of those federal holidays because the markets are closed. And so in this particular case, the reporting period is from November 13th, 2017 to November 13th, 2018. So it's 1 year's worth of data. And so the data in particular that's typically reported by these services is the date, of course, because you want to know what the trading day was, the closing price, the price at the close of the trading window at 4 o'clock in the afternoon, the volume, how many shares were either bought or sold, the opening price, what the price was when the market opened. I think it's 9 or 9:30 when the market opens on Wall Street, the highest price for the day and the lowest price for the day. And so the highest and lowest price aren't necessarily the price at the moment. It's just what is the peak that it reached for the day and what is the low it reached for the day. And that's a proxy for standard deviation. How wide is that variability? So nonetheless, we have this information from Yahoo Finance that was downloaded, and we loaded it into a data frame. And this set of options here is just another way to get it to parse your dates. And so before we said parse dates is true, and we gave it the index column. Now in this case, the date field is lowercase d for date, and it has to be the same capitalization as what's in the header row of the CSV file. But then here for parse dates, we don't have a Boolean, we have a list of the column names that it's going to use to get that date information when it interprets it. And so there are many different ways you can get the same behavior, and I'm trying to show you more than just one way to do it. So we pull in to a data frame by reading CSV, our year's worth of data for Apple scraped from Yahoo Finance, and we parse the date using the default North American interpretation or representation for dates, and it's going to come from the date column. And so we display the first 5 entries, and we can see here 2018, November 13th, 2018. And it's just the first 5, but it's each of the days. So the 13th, the 12th, the 9th, the 8th. So it goes backwards in time. Because when you produce a stock report, at the first measurement is always the most recent time in that span that you queried. Okay, any questions? Does that make sense? All right. So now, what are we going to do with this? Suppose now we want to know these aggregate numbers on a yearly basis. Okay, well, if we go from 2017 to 2018, we only have 2 years represented. Those months from 2017 and those months reported from 2018. But as we said before in the previous slide, a security is only traded 5 days a week. And if you have a federal holiday on any one of those weekdays, it doesn't trade. So in this aggregation, we say data frame, resample. So we produce one of these resampler objects, and the rule we give it is yearly. So it goes through and it pulls together all of those trading days in 2017 and all of those trading days in 2018. And so now we take that container and we go ahead and say, okay, compute the mean. Now we have a new data frame where each one of the columns that we had before, the series in the data frame, is no longer the original closing volume, open, high, and low information that we had. It's the sample mean for each one of the years in the reporting period. Any questions? Does that make sense? Yeah. Okay. And so if we can do that on a yearly basis, because it's a publicly traded company, it's very important to know this for the quarterly basis, which is exactly what they do when they issue their quarterly reports as required by the Securities and Exchange Commission, or SEC. So again, we read in this CSV file into memory, construct a data frame, and then we resample, aggregating on a quarterly basis, rule equals Q, and then we ask for the mean. And so now, if I direct your attention to this date field, again, excuse me, we're replacing the default index 0, 1, 2 with the date. And the date gets adjusted on a quarterly basis when we do this resampling and produce the mean. And so you'll see here, we have December 31st, 2017. So we started Q4 2017. The next one, we have March 31st, 2018. That's the first quarter in 2018. And so every 3 months worth of data in our reporting period of the original CSV file that we scraped from Yahoo Finance is represented, and it adjusts the index, the date, in this case, accordingly. Any questions? Does that make sense? So there are all sorts of aggregations that you can do. And in fact, the finance industry was very heavily involved in the creation of the Pandas API. So you see a lot of finance-like things in Pandas. Okay, and so something akin to that chart that we saw from Yahoo Finance with the volume underlay, we had these bars representing the volume. You could actually produce something like that. And in this case, we're going to do it on a quarterly basis. So again, we take our data for the original reporting period, 1 year's worth of data. We're going to go ahead and we're going to replace the default index. So index column equals date. And we're going to tell it to use the default interpretation, North American default, because that's the locale for my operating system on my laptop. We're going to use the North American format for parsing dates. Okay, so we take our original data, we re-aggregate it on a quarterly boundary, and then we go ahead and we take the mean. Now, once we take the mean, we get a data frame from that. I call it the mean, so I assign it to that variable. And now you can use data frame slicing on the result. So I go ahead and I get the closing price column for my re-aggregated data with the means on a quarterly basis. I get my volume information, and now I produce a subplot. So I'm going to produce a line plot for the closing date, price, and that's the average closing price for the quarter. And then I produce a plot for a bar with a bar chart for the volume, and that's the average volume per quarter over the reporting period. And so here we have our plot here, and you'll notice the quarters Q4, Q1, Q2, Q3, Q4, right, accordingly. And then you'll notice here on the bar chart, because it was a data frame, it's using the keys associated, the date or the indices, as my horizontal labels, and the tick marks on the vertical labels are the data representing the means for the volume. And of course, you'd have to have the right units reported as well. Any questions about this? Does that make sense? And so again, the thing I'm stressing here is that once you do this reaggregation and you compute some operation on it, the mean in this case, it gives you back a data frame. And as a data frame, you can now slice out or extract any column you want or any rectangle you want. Not only can you do the mean, you can do the median, you can do the quartiles, all sorts of different statistical APIs, anything that's available in the data frame, you have full use of after you do this reaggregation and this when you're trying to do the operation. Any question? Does that make sense? Okay. Another important thing is shifting quantities in time. Now, again, and you're going to probably remember this in your sleep, we go ahead and we're going to make use of the same Apple data from Yahoo Finance. And again, we tell it to replace the default index with the date column. And we're going to use the North American default for the date format. Now, in this case, suppose we wanted to take the closing price and we wanted to, for various reasons, we'll talk about on the Monday after spring break, various reasons you want to shift something in time. Now, this reporting period, we said when you report the closing price, it's reported for each day of the week, modulo any federal holidays. And so here we take our slice notation and we pull out the columns specifically for the closing price. And then we say, go ahead and shift this. Now, when you shift, you're basically taking your measurements and you're moving them one position in time for your reporting period. And so if the reporting period is on a daily basis, that report for the first day that you have in your table is going to be moved to the second day if you shift it 1 unit of time into the past. Now, when you perform this shift, this number, this parameter for the shift is the number of times you shift it 1 row in the table. If you have a negative number, it shifts in the opposite direction. It shifts up, starting from the bottom. Does that make sense? Any questions? Now you'll notice here, I'll direct your attention to the data. We have the closing price and we said shift 3 spaces. This 192 and 23 cents, that was in the 0th row, right? And so when you shift, if there's nothing above it to take that data when you do the shift, it'll insert not a number, right? Because there's nothing above this first entry. So if I shift it 1, 2, 3 spaces, we get not a number. Let me just okay. So when you shift from the top, it's a positive number. When you shift with a negative number, it shifts from the bottom. So if we said shift -1, whatever was originally in that last location for the last reporting period is going to move one row above. Does that make sense? Now, you might be thinking, why would I ever want to shift? We'll talk about that on Monday, I think it is, after a break, when we talk about so-called leading indicators and lagging indicators. Specifically, we'll talk about the Baltic Dry Goods Index. Okay, any questions? Does that make sense? Yeah. All right. And so the last thing that we'll talk about today is smoothing. And smoothing is really, really important. When you see a stock chart, that security and certain other types of measurements, they can wiggle quite a bit or deviate over the course of a day. Now, on real-time trading platforms, you can get quotes about 4 times a second, right? And so on a small time granularity, the stock price over small time scales is going to vary quite a bit. Now, when something varies quite a bit over the course of a reporting period, sometimes it can be very difficult to get a sense of the more general trend of where the price is going or where the measurement is going. And what you're concerned about is more macroscopically, is it going up or is it going down, sloping up or sloping down, or remaining even, and not so much the fine details about how it rises and falls. And so a smoothing operation is an operation like the sample mean that removes some of that variability. And so when you do smoothing, you're replacing each measurement with values of measurements that came before it within some window of observations. And so the mean is a type of smoothing operation. That's not the only one. We'll talk about exponential decaying windows and other operations. But in this case here, we read in the CSV that same data set for 1 year's worth of data for Apple stock price. And we're going to, again, replace the default index with the date entries for each measurement. And we're going to specify the North American default, again, for how you interpret the date format. Now here, we take our data frame and we slice out the closing price. That's the one we're interested in. It doesn't really matter which one, but I have to pick one. And then we go ahead and call rolling on that closing price. And what that rolling represents is if you have a measurement, looking for the chalk here, if you have some measurement 1, measurement 2, measurement 3, 4, 5, 6, etc., rolling means you take some window of observations. In this case, we have 3 observations, and we have the first, the second, the third. And in the next time instant, we move our window to drop the first measurement, but pick up the next measurement. So in this case, we have measurement 1, 2, 3. In the next instant, we have measurement 2, 3, 4, and then 3, 4, 5, etc. So that's what's called a rolling window. And sometimes in the literature, they just call it sliding window. And so when you have a rolling or sliding window, you can compute all sorts of statistics over the measurements in that window. So you could compute the mean, you could compute the median, you could compute all sorts of operations. Now, of course, your window, if it's very small, it's going to be smoothing, yes, but the amount of smoothing has some diminishing returns. The wider you make the window, what ends up happening is that the value you're computing incorporates more of the other values around it. And so values that were unnaturally high are going to get smaller when you take the average. Values that were unnaturally small are going to get larger when you take the average. And so these operations, like the mean over a rolling window, have a tendency to reduce the variability of what you're reporting. So we take our closing price, we have a rolling window, 5 measurements wide, and we say go ahead and take the mean, the sample mean of those 5 measurements. And here we say, okay, well, I'm going to create a new column in my data frame. And in data frame, it's really easy programmatically to insert a column. You could call the insert operation, yeah, or you could just assign. So here we have a new name, new column name, 5-month roll, and that's going to be the result of a rolling window, 5 measurements wide, where we take the mean, the sample mean, on those measurements in that rolling window. Does that make sense? Okay. So if we look at the result here, I said go ahead and display the first 10 entries of this rolling window. You notice for 5-month roll, the first 4 entries are not a number. Now, the reason for that is I'll direct your attention to the closing price. If we were to measure 5 measurements wide, ending in that first position, well, 5 measurements wide in that first position, there's nothing here for the first 4 measurements. Okay, so what do if there's nothing there? You just say, not a number. We don't have enough measurements to fill that window with 5 entries. So then you move that window down, you slide it. It's a rolling window. So now we have the first measurement, the second measurement, and 3 empty spaces. What do? Still not a number because you have these 3 measurements. So once you get to 4 of them, okay, you have 4 data containing entries in that window, but that first one is not a number. It doesn't exist. You don't have anything. So you use not a number. It's not until you get to the 5th measurement, 1, 2, 3, 4, 5, not until you get to the 5th measurement that you have data in each one of those positions in this 5-position rolling window. And so that's why you see here that 5th entry is the first place we have an actual value, because you can't take the mean of a nothing number. Does that make sense? Okay. So when you do these rolling windows, one of the pathologies is that the first n minus 1 entries are going to have not a number. So then what do? Well, that's where your data cleaning comes in. Now, in this case, the unadulterated data didn't have blemishes. A process or transformation you applied to it introduced new blemishes. You still have to make a choice about what you're going to do with those not a number entries if you want to report using it. Any questions? Oh, make sense? Yeah. All right. So the window size controls the amount of smoothness. And of course, when you do this rolling window, it replaces each measurement with the result of that window for all of the measurements behind it. Okay. So here's an example with our Apple stock, and this is to show you the impact of what a rolling window or so-called smoothing window does to your data. So I won't repeat again what the reading the CSV is. We pull it into memory, into a data frame, and then we construct a rolling or sliding window of 5 measurements wide, and we're going to compute the mean over those measurements. The choice made here is to take our not a number entries for the resulting smooth representation, and we're going to replace them with 0. Likewise, you could also replace them with the mean of all of those entries for the transform data. So now that I do that, I either have 0 or the smooth 5 measurement window over the data set for the reporting period. And so now I'm going to construct 2 series. I'm going to slice out the original closing price, the 5-month rolling window, and I'm going to plot the 2. And so in the blue, we have the original data. And in the red, we have the smooth version. And what you'll see is the blue curve is a lot more jagged. It spikes and drops more rapidly, but the red curve kind of turns more smoothly. And if I were to do a window size of 6, of 10, of 20, if I had enough reporting periods, you'd see that red curve get more and more smooth. Does that make sense? And so why do you care about smooth curves? Well, if you're looking at the blue curve, yeah, you're concerned that the stock rose and fell, but you're not concerned about all those little details on a single day's boundary or on a 1 minute boundary, right? You'd stress yourself out looking at stock, making trading decisions on a 1 minute boundary. What you care about is the more longer time scale or macro scale behavior. And the larger the smoothing window, the more smooth you're considering or you're making your graph. And you're seeing these trends along or relative to a larger time scale. Does that make sense? Any questions? All right. So here are some examples, and I want to get into the Jupyter Notebook. I have all the data files that I talked about today, as well as examples of these various time operations on the Canvas site. So here we have Costco. Costco is a national membership-based big box retailer. They focus primarily on food items, but they also have dry goods. Its ticker symbol is COST, and the reporting period is from October 12th, 2021 to October 12th, 2022. So it's a year's worth of data. So this is what their chart looks like, scraped from Yahoo Finance. And if you go on these platforms, you can select it and show it, but you can also download a CSV file, which contains the opening price, closing price, volume, high and low, and the trading date. And this is ExxonMobil's chart for the same reporting period. ExxonMobil is one of the world's largest energy companies. Oil and gas is their primary focus, but they do other stuff. And again, you can go on Yahoo Finance, select the reporting period, and download the CSV file. So here, this is Costco. We construct a 5 measurement wide smoothing window or rolling window. And we go ahead, like we did before. In the blue, we plot the original closing price. And you'll notice here it's closed with a capital C because that's what the CSV file had in it as the column header. And we plot in the red the smooth version. And if I were to change the window size, you'd see that red graph get more and more smooth and follow less and less all the details in the blue graph over time. Okay, any questions? No questions? Okay. And so this is ExxonMobil. You can see the price. And I did the same thing. In the blue is the original closing price, and the red is the 5-day rolling average, or the 5 measurement rolling average. Okay, so here in this chart, we depict the smooth version of the Costco security over the reporting period and the smooth version of the ExxonMobil security. Now, of course, one analysis you might want to know is how does the price of oil impact the price of these food items as well as durable goods. And so one measurement you might make is the correlation. So in this case, you're doing the correlation between the smooth version, the 5 measurement or the 5-day rolling average, and of Costco, and the smooth version by 5-day rolling average of ExxonMobil. And so we have the two charts here, and then we compute our correlation. And so here we're taking the smooth version of Exxon, and we're saying give us the correlation with a smooth version of Costco. Now, of course, in the Python notebook, the correlation I'm specifying the same correlation that we talked about, which is the so-called Pearson correlation. But there are many other correlations that we will talk about in the future that are useful for certain types of data. Okay. Any questions about this? Does that make sense? Yeah. All right. So let's take a look in the next 10 minutes at the Jupyter Notebook. And I'm going to pop out of PowerPoint here and go to the Jupyter Notebook. And every time I exit PowerPoint, it loses the share. So I'm just going to share screen and reshare my Jupyter Notebook. And I also have up in the background here, this is the documentation of record for the DateTime index. And if you go to the DateTime API library, you'll see in all its splendor and glory all the different options you can have for your DateTime and time-based APIs. There are just too many of them to talk about in the course of a semester. So that being the case, let's bring up the Jupyter Notebook. And we're going to start out with our imports. And then we're just going to construct a date object and a time object like we had in the slides. And you get, of course, a date format in the default, which is North American representation. And here, you'll notice here, I'll just direct your attention for microseconds, 125, 123, with the decimal point for the microseconds. Here is an example of date time now. Of course, that changes each time you run it. So now it's now 10:06 and 49 seconds with some microseconds. So here we're going to have different resolutions. Here we have a date time object that we're constructing. The full construction that includes down to the microseconds. So if we go ahead and construct that and print it out, of course, it's March 3rd, 9:25, and some microseconds. If we leave out microseconds, we still get our date time object. And you notice here in the printout, there's no decimal here on seconds, right? We could go a little further than that, and maybe we leave out the seconds. We only have hours and minutes, and you'll see here the seconds field in the time portion of the date time object print is truncated to 0, or the defaulted to 0. And then likewise, if we just have the date and we don't specify hours, minutes, seconds, or microseconds, it still has to print a value. And so it sets as using the default value of 0 for both the hours, the minutes, and the second. And microseconds, you'll see there's no decimal on the seconds field. Okay, any questions? That makes sense? And I encourage you to tinker with this yourself. If we do date time now, and now it goes to my system clock and it gets the current date and time. And if we have now 2, and I think I had now up above. And so it's been 1 minute and 17 seconds from when I first called now to the second time I call now. And you could have a computation, and before your computation starts, maybe you're doing some processing, you call date time now, and then after your algorithm is done, you call date time now again, subtract it 2, and that's the wall clock time for your computation to run. This is not as precise as relying on other facilities, but it's good enough for the purposes of this class. If you're doing performance engineering, it's really important to tease apart what aspects of your program contributed to the total wall clock time. Okay, so there's another date, and we did that subtraction. And if it had days, not just hours, it would give you the full algebra and actually tell you how many days, how many hours, how many minutes, how many seconds, and how many microseconds, if that's useful to you. Here's an example of talking about that now snapshot instant in time and time delta, so 7 days ago. So we print out that difference, and it gives us instant in time. So that's a time delta of 7 days. Now we subtract. It was February 24th at 10:06 and 49 seconds and change. Any questions? No? All right. So this is the date range. This would have been very useful, but it was on purpose for project number 1. You call date range in Pandas, and I still don't know why it's in Pandas and not in DateTime, but go figure. And if we print that out, of course, we get the dates. We could change the start time and the end time, and it'll adjust appropriately. And I'll direct you to the API documentation for Pandas date range for all the options for the different types of boundaries for start and stop that you can start and end that you can specify. It'll count for date ranges and time ranges. I just don't know off the top of my head, and I don't expect you to memorize all the different several dozens of options you can specify. So nonetheless, you can get the date time index, and now you can do other algebra with this, like get the min, get the max, get the median, and stuff like that. So now we'll go to vehicle sales, and we'll read that in and show the first 5 through head of the entries in the CSV for lightweight vehicle sales. Useful thing to do is to measure the shape, 561 rows and 1 column. We can resample on a quarterly basis. If I do that and then do the first 5, show the head of this list, we see that it ends on the quarterly boundaries. So we have March 31st, June 30th, September 30th, and December 31st. And then it wraps around to the next year, the first quarter, which ends in March. Okay, any questions? Does that make sense? Yeah, all right. So now, this is just to show you the data type, the object type that it constructed when we did this resampling. It's a date time index resampler. And again, this is an object that contains a set of lists where each list has data rows corresponding to certain time boundaries that you specified when you did the resample, called the resample API. In this case, it's quarterly, every 3 months worth of data. And so whether your original reporting was on days, on seconds, on hours, it'll aggregate all of that on a 3 monthly basis on quarterly boundaries. Okay, so this is the Apple data. And we show the head of this list, scraped from Yahoo Finance. Again, we have the date field, closing price, volume, open, high, and low for the security. In this case, we're going to re-aggregate it on a yearly boundary for the reporting period. And then we're going to take that date time index, that container, and we're going to compute the mean. And so this is on a yearly basis, and this reporting period was each month over 2 years. And so we're only going to have 2 entries, one for the year ending in 2017 and another for the year ending in 2018. Now, of course, it does it for each one of the original columns. So this is a full data frame that it gives you. And now you can slice this as you would any data frame or call any other statistics on it that you would with any other data frame. Okay, any questions? That makes sense? Yeah, all right. So now we do it again on a quarterly basis. And now it's on the quarter. Before we had year, it was only 2 years. But the quarters, we have the fourth quarter, 2017, first quarter, 2018, second quarter, 2018, third quarter, 2018, and so forth. And again, this is a full data frame. And so this container, you can't really do much with it. You have to calculate something on it. And then once you calculate something, in this case, the sample mean, it gives you a full data frame with that sample mean, in this case, for each one of those columns that you originally had. Any questions? Does that make sense? No? All right. So then let's see. By quarter, and can't remember why I did that. Oh, we're going to plot. Okay. Plot it by the quarter. So here, now, I compute the mean for the quarterly data, and I'm constructing, oh, okay, that's fine. I want to show you an example of slicing. Another way you can slice a data frame, you can do it by single column key name, or you can have a list of column key names. And so here we're slicing 2 columns, the closing price and the volume. So now that we have that data frame, I'm going to go ahead and slice out the individual columns. I don't know why I did it again. And then I'm going to plot the closing price. And you can use as the x-axis tick marks the indices. In this case, the indices are the dates, because that was what we told Pandas to replace the default index with this date column. And then the values here, we're actually accessing the dictionary underlying the data frame that we just returned. And so here, values are the list of that closing series, and index, that's the replaced default index, which are the dates. And so if we do that plot, we see our plot here. These are the quarterly means. And then here along the horizontal axis, we have the indices, which are the dates for each quarter. So year ended Q1, Q2, Q3, Q4, etc. And then on the horizontal axis, these points on the graph, those are the actual sample means for each quarter. Any questions? No? All right. Oh, and we're out of time. In the interest of time, I want to always respect your time. I'll stop there, but we'll do some subplots later, and we do exactly everything here in Jupyter that I showed you in the PowerPoint. So I encourage you to tinker with this. Let me stop, and I will not keep you from your spring break, or if you have another class, they'll be keeping you from your spring break. So